Action.
Action. Okay, so we're going to extend our idea of kinetic energy to include objects that are rotating as well as objects that are just translating. And conveniently, if we think about our linear quantities and like their rotational kind of partners, it's exactly the same equation. The linear one's half mv squared. The rotational one, we swap mass for inertia and we swap angular velocity for normal velocity. We've got exactly the same equation, and it works out because it used to be speed squared, and that's like meters squared per second squared. Now we've got the meters squared in the inertia, and we've got the like per second squared in our angular velocity. So same equation. And it seems really simple, eh? And so then we apply it to like the situation we just saw. What if there's someone like on the rotating platform with the masses outstretched and they're rotating around, and then they bring those masses in, their inertia halves, and their angular velocity doubles? What happens? So if we think about the EKR initial, we've got half I omega squared. But if the angular velocity doubles and the inertia halves, our EKR final is going to be half, inertia's halved, so half inertia, omega has doubled, so 2 omega squared. That's some ugly maths. What do we do? 2 squared, what's that? 4. What's half of 4? 2. And half of 2 again? 1. And so the EKR final is just I omega squared. What we notice is that's 2 times EKR initial.
Wait, true.
Ooh.
What is going on? We just
I could have told you that.
our rotational kinetic energy. We just created energy from nowhere.
No, because didn't we require energy to bring the masses in?
We required energy to bring the masses in. So if you've ever been in that position of needing to bring the masses in, we know that what they would like to do is keep going in a straight line, and it's the tension in your arms that's providing the centripetal force to keep them moving in circular motion. If you want to decrease the radius of that circle, you have to do work on those masses to pull them in. Work is transforming energy from one form to another. What you're doing, whenever we're changing the inertia of something, if we're decreasing the inertia of something while it's moving, we're doing work on it to change that inertia, and we see that work appear as an increase in the rotational kinetic energy. And the opposite applies. If something spreads out while it's rotating, that's the tendency that it's going to do, like the thing it's going to do naturally. If it's kind of like a not rigid object, it will just kind of spread out, and that will decrease its rotational kinetic energy because some of the rotational kinetic energy will have done work on it, moving it apart. Does that sort of make sense? So beware the rotational kinetic energy. It does weird things. Like if a satellite's spinning and then it retracts its solar panels, weird things happen to the kinetic energy, and we have to think about, oh, maybe its battery has used up some energy to create that change, or as the solar panels have moved out, maybe the batteries are being charged a bit. Weird things happen. So energy is always conserved, but expect that when we have these conservation of angular momentum situations, we're not going to get the rotational kinetic energy.